Good afternoon, everyone. As you all know that to mark the 75 years of India's independence, Government of India is celebrating Azadi Ka Amrit Mahotsav. The Indian National Science Academy is also celebrating Amrit Mahotsav by organizing several programs, and today's lecture commemorating Professor M.N. Shaha's is also part of it. The lecture session will be chaired by Professor Chandrima Shaha. Dr. Saha is a biologist. She is President, Indian National Science Academy, and J.C. Bose Distinguished Chair Professor of National Academy of Sciences at the Indian Institute of Chemical Biology, Kolkata. I request Professor Chandrima Shaha, President INSA, to welcome the guest and introduce the speaker.
Thank you very much, Seema. I will, I think the introduction part will be given by Dr. Notia. I will say a few words about Professor Saha. I first would like to welcome all of you to today's lecture by Professor Arnab Choudhuri. It's very kind of him that he agreed to accede to our request, and so we are actually waiting for a feast. But prior to when he explains Meghnad Saha's work, I would like to provide a little history about Professor Saha, because it's always interesting to know the sort of character of a man, or what he has done all his life before going into his science. We know that he was a great scientist, and Dr. Arnab will detail on his work. And this is the time for Azadi Ka Amrit Mahotsav. It is 75 years of Indian independence, and celebrating our independence also is remembering people who contributed to the freedom movement and also the growth of the nation. Prior to post-independence, one of the towering figures in science was Meghnad Saha, a man much ahead of his times. With phenomenal contributions in astrophysics, Professor Saha was a great patriot at heart. He supported the movement against colonial rule, and his abode at Kolkata was a rendezvous of many revolutionaries. Prior to that, history of his younger days records that he was expelled from school for taking part in anti-colonial movement. Born in 1893 in Dhaka district of erstwhile East Bengal, or to poor parents, he had to struggle to get education. His life had many struggles, with growing up amidst extreme financial hardship, and later in life against strong non-cooperation from the administrative authority during the colonial rule. He graduated from collegiate school in Dhaka, and after passing the intermediate examination of the Calcutta University in 1911 from the Dhaka College, Professor Shaha joined the Presidency College at Kolkata. And it was a time when many greats were there. So among his classmates were Satyendra Bose, Prashant Chandra Mahanalavish. His teachers were Prafulla Chandra Ray and Jagdish Chandra Bose. So you can imagine the kind of atmosphere that was prevailing at that time. Eventually, he got a fellowship, the Premchand Roychand Scholarship, that enabled him to go abroad. This is a photograph, which is a farewell party for him before he went to England. Actually, he went to Germany, sorry. And so this was in 1990. First, he went to London, where he was with Alfred Fowler, subsequently moved into Berlin, where he worked in Walter Nernst's laboratory. Upon his return from Germany in 1921, Professor Shah was at the heart of politics of scientific development in India, planning for the independence of the nation and the scientific community. He struggled to change the conditions of science and aspired to build a kind of scientific community that he has experienced in Europe.
So excuse me, I am unable to see the screen. Are you sharing this photograph or other things?
Yes.
Can others see? Can others see?
Sir,
No, we are
Shiv Udavchand has to stop the screen sharing there so that others can see.
I also cannot see the screen. I thought Chandrima doesn't want to show.
No, I was sharing the screen. So
No,
Seema,
but
can you unshare?
nothing visible.
No,
Okay,
we
just-
cannot see the screen.
Just a second, then I will start sharing it again.
no, we are seeing his screen, somebody's desktop.
Share.
This is
Professor
ma'am.
Shiv Udavchand has to stop sharing. Yeah, now it is okay.
Ma'am,
Yeah,
you
somebody
share
else was
the
sharing.
file.
Yeah.
Share the file.
Can you share? Can you see my screen now? 75 years.
Yes.
Now
Now
it
we
is
can,
seen.
yeah.
Now it is seen.
Okay. So I was what I
Are you muted?
Mute.
Ma'am, you have to unmute yourself, please.
By accident, she must have.
I think you
Ma'am,
have
please
muted.
unmute. Madam, please unmute.
Professor Shaha, please unmute yourself.
Yes, I have unmuted myself. I think I
Okay,
was
now,
centrally
now.
unmuted, centrally muted. So
Okay.
yeah, I was talking. Now you can see my screen, right?
Right.
So I was here that I eventually Professor Saha got the Premchand Roychand Scholarship of Calcutta University to go to London and then to Berlin. And so he, this is his a photograph of his farewell party, where stalwarts like S.N. Bose, C.V. Raman, Meghna Shaha, and just beside him is D.M. Bose. So all you can see the title below, the caption below, and here you see so many of very very bright people, very bright scientists were there together with him at that time. So the times were very exciting. So he, till about 1930s, Professor Shaha was fully involved in research and teaching, and thereafter he stepped out of the ivory tower by his own admission and tried to look at how scientific research and communication should evolve in the country. His view was to have a platform where scientific thoughts could be exchanged and ideas disseminated. His views were published in the December 1929 issue of University of Allahabad magazine. He was with University of Allahabad, where he built a really strong department. And he actually proposed a plea for an Academy of Sciences. And finally, he established the Academy of the United Provinces in 1930, while he was professor of physics at Allahabad University. So the UP Academy of Sciences was later named as the National Academy of Science. He said that an Academy of Science can do a great deal by educating public opinion, undertaking particular problems, and bringing out scientific workers in various fields for discussion and cooperative research. But the main function of the Academy should be towards cultural improvement by contributions to human knowledge. This is what he said in his address, the first address that he gave. So then he was also instrumental in creating what is INSA today. In 1934, a special meeting of the Indian Science Congress Association was held on the appeal of President of ISCA, which was Professor Meghnad Saha at that time. He sought support for an Indian Academy on the model of Royal Society. This proposal was unanimously accepted, and the foundation of the National Institute of Sciences in India, which was called NISI, which was an all India body, was thus laid. The first meetings of NISI were soon held in 1935 in the Senate Hall of Calcutta University, and L.L. Farmer was elected as the head of NISI until Professor Shaha became chairman in 1937. So he was actually instrumental in creating 2 academies of sciences in India. So this is INSA in New Delhi now, and this is the Institute of Nuclear Physics in Kolkata. So the NISI, when it was created, which I forgot to tell, was actually operating from Asiatic Society in Kolkata. Subsequently, it shifted to Delhi. And that was again by Professor Shaha's own, enthusiasm that it was shifted to Delhi. So his vision to create an Institute of Nuclear Physics was realized when the foundation stone was laid in 1948. The building was officially opened in January 1950 by Frederick Joliot-Curie, head of the French Atomic Energy Commission. I think it was his wife also, Irene Joliot-Curie, who actually opened it. So they were visiting India at that time. So at the invitation of the institute. So it is not only the institutions he created, but through his reach in governing councils of many of these institutes, he actually modeled them in very, I should say, very enthusiastic way in the model of any European institutes that he has seen at that time. So the Indian Association of Cultivation of Science was founded in 1876 by Mahendralal Sharkar, who was an acclaimed medical practitioner. And C.V. Raman made his historic discovery in this particular institute. So this was the old building of Indian Association of Cultivation of Science and the new building that Professor Shaha actually initiated building. So this association actually embarked upon a new development plan under the dynamic leadership of Meghna Shaha. Now, he envisaged the creation of an active research school for investigation in the problems of continuing with the fundamental studies of X-rays, optics, magnetism, Raman effect, in which the association has specialized in early years. A new campus was opened at Jadavpur, and we all know that it's a sprawling campus right now. So in 1942, Professor Saha created another institution, the CGCRI, which is also in Jadavpur. And he argued that if glass industry in India has to be placed on a firm basis, it is of immediate importance that there should be a school of glass technology in a suitable center, which will arrange for adequate and effective provisions for training and research. So this institute was actually established. In 1952, he was actually elected as member of parliament as an independent candidate from the Northwest Calcutta constituency. Welcoming Saha's election, Professor Halden said that, "May I also be allowed to congratulate him on his recent successful re-entry into politics. India needs men who will bring some understanding of science to the government of the country. Even those who do not share his political views may rejoice that he can make his voice heard in the Council of the People." This was J.B.S. Halden who said that. So in addition to his creation of these institutions, he also was the editor of Science and Culture, which was published to another association that he created, which is Indian Science News Association, ISNA. And he was its editor until then. It was established with the objective to disseminate science news as well as reflection of the community of Indian scientists and thinkers for public understanding of science and culture together. So what he did was he made Allahabad University a world-class university, created the Institute of Nuclear Physics at Kolkata, created Indian Association for the Cultivation of Science, created or made it into a world-class research organization, created the CGCR at Kolkata, and was responsible for eventual creation of Positional Astronomy Center at Kolkata, and was also responsible for creation of 2 science academies of India, the INSA and the NASI. So here was a man who has created all these while doing excellent science. So it is indeed amazing that one person could contribute so much to the development of our nation. And it is very difficult to imagine what more he could have achieved had he not died at the early age of 63. So this was a little background that I just gave to prior to Professor Choudhuri's talk. And I hope I'm trying to stop sharing my screen. Yes. Yes. So, Dr. Naughtiel, can you give an introduction to Dr. Choudhuri? Yes.
Thank you, Professor Shaha.
for a beautiful illustrative presentation. It's an honor to introduce Professor Arnab Choudhuri, who is a professor of physics at the Indian Institute of Science, Bangalore. He did his graduation and post-graduation from prestigious institutions, namely the Presidency College at Kolkata and IIT Kanpur. He did his doctoral work at the University of Chicago under a person whose name has become synonymous with solar physics, that is Eugene Parker, who gave the famous magnetohydrodynamic equation. He returned to India in 1987, and he started working and teaching at Indian Institute of Science, and that is where he stayed since then. Professor Choudhuri has worked on the formation of sunspots and also on the well-known 11-year sunspot cycle. And he was the man who proposed the famous and now relatively well-accepted flux transport dynamo model, and which is one of the most popular models about sunspot cycle. He also wrote 2 advanced textbooks, and one of those books has also been translated into Japanese recently. He also wrote a popular science book whose name is Nature's Third Cycle, A Story of Sunspots, and it was published by Oxford University Press. He has been interested in how research in physical sciences began in colonial India, and his today's presentation, is also somewhat related to that on the work of Professor Meghnad Saha. But I'm sure that this is not going to be any dull or drab story of man's conquest from a very, very poor, handicapped background to the pinnacle of success in science and also perhaps in politics. And Professor Choudhuri would be describing the tribulations and travails of Professor Shaha. Professor Choudhuri is an elected fellow of all the 3 major science academies of India, as well as the World Academy of Sciences. And he has been an Alexander von Humboldt Fellow and also a J.C. Bose National. Pleasure to invite Professor Arnab Choudhuri to Professor Choudhuri.
Yeah, we can see this slides.
Yeah, we are able to see the screen.
Dr. Raichaudhuri, can you make it full screen?
Yeah, so you are able to see the screen?
Yes, we can see it.
Yeah.
We can see it very clearly.
Okay, and
Yes.
can you hear me clearly?
Yes,
Okay.
now we can hear you clearly.
Okay. So I thank Professor Chandrima Shaha for inviting me and Dr. Nautiyal for the very kind introduction. So it is a great honor and privilege for me to give this special lecture on the occasion of Meghnad Shaha's birthday during this Azadi Ka Amrit Mahotsav year. So as Professor Chandrima Shaha pointed out that Meghnad Shaha was a really multifaceted genius who made enormous contributions in different fields, including this establishment of organizations like INSA. So if a speaker has to do a proper justice to all of his contributions, then the speaker also has to be a multifaceted person to understand the significance of all his contributions. So since I do not have the capability of doing that, so I decided to focus only on Meghnad Shaha's most famous scientific work, Saha Ionization equation. So this is a work on which the first paper appeared in Philosophical Magazine in 1920. So I show the beginning of the paper. So last year was the centenary year of this outstanding work. And if you look at Meghnad Shaha's birth year and also the year of publication of this paper, then you realize that he did this work when he was barely something like 26 years old. Now at the age of 26, typically a youngster aspiring for a scientific career would be learning the research techniques under the guidance of a supervisor. But it was at this tender age of 26 that Meghnad Shaha, working at Calcutta University, far away from all active centers of physics and without any supervisor, formulated his theory of thermal ionization and revolutionized astrophysics. So this theory of this Shaha ionization equation is a standard topic in a course of basic statistical mechanics, which all physics MSc students have to take. So anybody with an MSc degree in physics would know what this equation is, or also would know how to derive this equation from the fundamental principles of statistical mechanics. But even such persons may not know what was the exact nature of Meghnad Shaha's contribution in this field. Was he the first person to derive this equation? So it came as a surprise to many that he not only did not derive the equation, he was also not the first person to write down this equation. So what we now call Shaha ionization equation appeared at least in 2 papers by Agar and Lindemann before Shaha's first paper on the subject. So how this theory developed, that has many twists and turns, which I shall try to describe. So now I shall try not to be too technical in a lecture of this kind, but let me give you a brief explanation of what Shaha ionization equation is for those who do not know about it. So all of us know that an atom consists of a positively charged nucleus around which negatively charged electrons would be going around. The simplest atom is a hydrogen atom with a proton as a nucleus and an electron going around it. There are situations when an atom may lose an electron. Then the leftover part of the atom, which will have a net positive charge, is called an ion, and this process is known as ionization. So as we heat a gas, we find that more and more atoms get ionized. And this is the Shaha ionization equation as given in his first paper. So this equation tells you how one can calculate the fraction x of atoms which have become ionized at a particular temperature T and a particular pressure P. So if you know T and P, then you should be able to calculate the ionization fraction x, provided you know this another quantity u, which I shall explain later. And Shaha ionization equation also shows that when you increase the temperature sufficiently, virtually all the atoms get ionized, and that sort of state of a gas is called a plasma state. So this equation also gives the transition how neutral gas gets converted into a plasma. So it is also one of the fundamental equations of plasma physics. Okay, the first 3 decades of 20th century happened to be an era of scientific revolution in physics based around quantum theory and relativity. It is often not realized that this scientific revolution was achieved by a very small number of persons working in this very small geographical region of Europe. It was almost like a close-knit family affair, and most of these people knew each other personally. They often traveled to meet each other and attended conferences like Solvay conferences, and many of them had the habit of writing letters. So in that era of efficient postal service, probably a letter posted in any city within this region would reach another city in a day or two. So even in that era, many years before internet and email, the news of a major scientific breakthrough would spread through this closely knit family of physicists very fast. And it seemed that it would be almost impossible for an outsider to break into this charmed circle from a distant land where journals would take several months to reach by slow surface mail. But very surprisingly, when this scientific revolution was at its peak, suddenly one after another, three extraordinary works came from a newly established physics department of Calcutta University. There's this Saha Ionization equation in 1920, and then Bohr statistics in 1924. So although I should mention that S.N. Bosch, who did this work, he shifted from Calcutta University to Dhaka University little bit before this work was done. So this work came out from Dhaka University, and then Raman effect was discovered in 1928, and because of which the first Nobel Prize in Science was given to an Asian in 1930. And perhaps the only other discovery pertaining to new physics, which was of such importance made outside Europe in that era, was Compton effect discovered in USA in 1923. So this is something I think totally without parallels in the annals of physics. It will be probably impossible to give another example that when such a scientific revolution was going on, suddenly I think three such important discoveries came from a distant land without without much previous background of science. So now analysis of such scientific creativity in a peripheral region raises many important questions in history of science and philosophy of science. So it is somewhat of a surprise that these issues have not been studied enough. Of course, human creativity is something very mysterious, which we understand very little. So one can give examples from other fields of human creativity, of sudden blossoming of genius in a particular place at a particular time. For example, in ancient Greece, three contemporaries, Aeschylus, Sophocles, and Euripides wrote tragedies which could not be matched for nearly 2000 years till Shakespeare wrote his Hamlet. Then again in Renaissance Europe or Renaissance Italy, three contemporaries, Leonardo, Michelangelo, and Raphael, created works of art which continue to amaze us. So nobody has been able to give any proper satisfactory explanation of why this genius blossomed in this manner in one place in one time. So the best we can do is to analyze the social conditions at that time, which might have been conducive for this sort of flowering of genius. And how can we reconstruct the history of such creative process in science? So usually the published papers are not too much of help, because a scientist puts only the finished product in a published paper, and usually the traces of the creative process are left out from the paper. So one has to look at other sources like the scientist's personal papers, his correspondence with other scientists, and his speeches and things like that. And unfortunately, in India, we are particularly bad in archiving such materials. But in the case of Meghnad Shaha, luckily his children preserved his correspondence with other great physicists, and which give us some idea of Shaha's scientific growth. Especially, we have two very long autobiographical letters which Shaha wrote to fellow scientist Plaskett, from which I shall be quoting. Okay, some basic information about Shaha, which Professor Chandrima Shaha also gave. So Meghnad Shaha was born in 1893 in a small village of Shauratoli, not too far from Dhaka. So his father had a small grocery store in the village, and nobody from that family had gone for higher education before Meghnad Shaha. but he came to Calcutta in 1911 to study in Presidency College, from where in 1913 he got BSc in Mathematics, and 1915 MSc in Mixed Mathematics, what we would now call Applied Mathematics. And Choudhuri Bose, who formulated Bose-Einstein statistics, was his classmate during BSc and MSc. And in fact, Choudhuri Bose got the first rank both in BSc and MSc, and Meghnad Shaha got the second rank. So when they completed their MSc, that was not a good time for the job market for science graduates in Calcutta, but somehow an unusual opportunity came up before them. So Calcutta University was established in 1857, the year of India's first war of independence. But for more than half a century, it was merely a body for conducting examinations and granting degrees without any core faculty. So it was the visionary Vice Chancellor, Sir Ashutosh Mukherjee, who started postgraduate departments with core faculty by utilizing funds which you could obtain from large donations of a few wealthy Indians. And Sir Ashutosh himself was a very capable mathematician who published papers in international journals at a very young age. But at that time, there was not much career opportunity for a mathematician in India. So Sir Ashutosh then moved to the legal profession. But he had a lifelong soft corner for mathematics and physics. And he also knew that this was an era of revolution in physics. So he dreamed of establishing a physics department where teaching and research would be done in quantum theory and relativity. And more or less all his well-wishers told him that this is a completely crazy idea, whereas at that time nobody in the whole of India who knew much of quantum theory or relativity. But Sir Ashutosh should not give up. He knew about an officer in the finance department who was publishing papers in international journals by working in the evenings and weekends. So Sir Ashutosh invited this person to occupy the main chair of the new physics department, the Palit professorship, and that person was C.V. Raman. And he knew that Meghnad Shaha and Sir Ashutosh needed younger faculty to teach. So he knew that Meghnad Shaha and Choudhuri Bose were brilliant students of mathematics. So he one day called them and told them that he will give them jobs if they were willing to learn physics and teach in this new physics department. And Meghnad Shaha was given the job of teaching quantum theory and Bose teaching relativity. And as one says, the rest of history. So here I again show this photograph of the physics faculty of Calcutta University at that time, which Professor Chandrima Shaha also showed. And she pointed out that this is S.N. Bose, this is C.V. Raman, and this is Meghnad Shaha. And you can see that it was the faculty was very small, just barely about a dozen persons. And some of the other persons also became very famous physicists. So that this was D.M. Bose, and this is Shishir Mitra, who was actually another of the past president of INSA. He did very fundamental work on upper atmosphere. And and while teaching, Meghnad Shaha also started trying out his hand in research. So if you look at the titles of his first few papers, then anybody who is familiar with MSc Physics syllabus will realize that his first few papers were more like extensions of what can be found in typically in physics MSc textbooks. So it took him about 3 years before he could find one niche area in which he could become a leader in the world. So Shaha has given the following account of his research preparation in his long letter to classmate. So I began from 1916 to read rather desultorily any book on physics, mathematics, and astronomy and astrophysics, which came in my way or could be found in the library of my old college, Presidency College, Calcutta, or in the library of the Calcutta University. I might add that I had begun to learn German privately as early as 1911 while I was a student in the inter-science class. And by 1916, I had enough proficiency to study scientific papers without the use of a dictionary. In course of the studies, I came across Miss Agnes Clark's two books on astrophysics, one on the sun, the other on stars, and this excited my interest in astrophysics and made me familiar with some of its problems. A year later, in 1917, the Calcutta University opened MSc classes in mathematics and physics, and I was asked to teach an odd assortment of subjects: thermodynamics, spectroscopy, figure of the earth, and was given the charge of the heat laboratory. I was asked to teach thermodynamics because no one else of my colleagues would agree to take up that unpleasant subject as they styled it. I had read no book on this subject previously. So as I shall stress later, this Shaha's work on thermal ionization required knowledge of some totally disconnected scientific fields: chemical equilibrium theory, atomic physics experiments, stellar spectroscopy. Presumably, a young person trained in an active center of science under a supervisor would be asked to specialize quite early and would not have the opportunity of reading acquiring knowledge about all these kinds of different fields. So probably Meghnad Shaha might have been the only person in the world who, because of his habit of this reading desultorily, as he said, that he acquired knowledge of all these different fields, and he was able to formulate this theory of thermal ionization. So it is often pointed out that a lack of formal training can be often helpful for the blossoming of genius, and Shaha's case is a striking example of that. Well, it was in 1911 that Rutherford established the nuclear model of the atom, and then it became clear that it's possible for an atom to lose an electron. And one person who was particularly interested in that was Eddington, who was trying to build models of stars. And one can easily estimate that the density in the interior of the sun would be several times the density of water. And normally matter exists in the solid or liquid state at that density. So most astronomers also thought that matter inside of stars would be in the liquid or solid state. And if that were the case, then it would have been very difficult to build models of stars, because I think solid or liquid states are very complicated states of matter. But Eddington realized that if many of the atoms inside stars are ionized, then they would obey this much simpler ideal gas law, and then it will be much easier to build models of stars. So in 1917, Eddington wrote in a paper of the hypothesis that the atoms are highly ionized, so that most or all of the electrons outside the nucleus have been broken off and move as independent particles. This suggestion that at these high temperatures we are concerned with particles smaller than the atom was made to me independently by Newell, Jeans, and Lindemann. By an argument which now appears insufficient, I had supposed that the atomic disintegration, though undoubtedly occurring, could not have proceeded very far. But Jeans has convinced me that a rather extreme state of disintegration is possible and indeed seems more plausible. So the challenge was to do a real quantitative calculation and show whether these many atoms inside a star would be really ionized or not. So John Agar is the first person who realized that one can study the theory of chemical equilibrium to study this problem. For example, consider the ionization of calcium. A calcium atom absorbs some heat U, and then it gets broken in a calcium ion, Ca plus, and an electron. And this is very similar to a chemical reaction that molecules A, B, C absorb some heat U and then get converted to molecules M, N, O. And if this reaction proceeds under a circumstance that the product molecules cannot leave the system, which will happen if the reaction takes place, if it's a gaseous reaction taking place in a container, or the reaction takes place in a dilute solution, then we can also have a reverse reaction, and we would reach a chemical equilibrium when the forward reaction and the backward reaction balance each other. And the theory of such chemical equilibrium was developed by scientists like Gibbs and Nernst. So what Agar did was that he took an equation from Nernst and cast it in a form suitable for studying this thermal ionization. So here is a paper from Agar's, here is a page from Agar's paper. And those of you who are familiar with Saha ionization equation would realize that this is a primitive form of that equation. And Agar realized that this U0 can be obtained from this ionization potential of hydrogen, this well-known 13.6 electron volts. So by using that, Agar was able to show that hydrogen inside a star would be ionized at that high temperature. And now we know that hydrogen is the most abundant element inside a star. But at that time, most astronomers thought that the composition of a star must be very similar to the composition of the Earth. So the important question was to do similar ionization calculations for other elements. And Agar had no idea how to do calculations for other elements. And another related work at that time was done by Lindemann, and who was studying magnetic storms. So often in the sun, we see large explosions called solar flares. And typically 3 or 4 days after a solar flare, we have a magnetic storm, which involves a very rapid variation of the Earth's magnetic field. So Lindemann assumed that during an explosion in the sun, an approximate equal number of positive and negative ions are projected from the sun in something of the form of a cloud, and these are the cause of magnetic storms and aurorae. So in the present day language, we would say that at the time of a solar flare, a chunk of plasma gets thrown from the sun, and when it reaches the Earth, then it produces geomagnetic storms. And several decades after Lindemann's prediction, these coronal mass ejections were discovered, and it showed that Lindemann was indeed correct. And to validate these theories, Lindemann had to show that matter in the sun's atmosphere would be in the ionized state. And Lindemann also could do the calculation only for hydrogen. And I may mention that apart from anticipating Meghnad Shah, Lindemann had another very unfortunate connection with India. So in later life, he was raised to peerage as Lord Cherwell, and he became the scientific advisor to Churchill during the Second World War. And he advised Churchill to adopt certain policies which led to a terrible famine in eastern India, Panchashen Manvantar, in which more than 3 million people are estimated to have perished. So historians identify Lindemann as the person who should be held primarily responsible for this terrible man-made famine. So anyway, let me now come to Shaha's work. So Shaha developed his theory of thermal ionization in a series of 4 papers. All these papers were submitted from while Shaha was in Calcutta University. But as Professor Chandrima Shaha mentioned, that then Meghnad Shah got this Premchand Raichat scholarship, with which he was able to come to England immediately after submitting his papers. So he came to the laboratory of Alfred Fowler at Imperial College London, and first three of these papers appeared one after another after Shaha reached London. But Shaha decided to withdraw this fourth paper and do some more work on this while he was in Fowler's laboratory, and eventually Fowler communicated it to these proceedings of a Royal Society. So those days only a fellow of the Royal Society could communicate something to the proceedings. And as I mentioned that Agar or Lindemann could do their ionization calculations only for hydrogen, because they did not know how to obtain this quantity U for other atoms. But Shaha figured out that one could get this quantity U for other elements besides hydrogen from atomic physics experimental data. So he wrote in his first paper, the value of U in the case of alkaline earths and in many other elements can easily be calculated from the value of the ionization potential of elements as determined by Frank and Hertz, McClellan, and others. So presumably Agar or Lindemann did not know much about atomic physics or these experiments. And also Shaha quickly realized that it was a subject of stellar spectroscopy, which was just almost waiting for a breakthrough by applying this theory of thermal ionization. Again, that had completely escaped Agar or Lindemann, because presumably they did not know anything about stellar spectroscopy. So let me say a few words about stellar spectroscopy. It was in 1817 that Fraunhofer discovered that there are some dark lines in the spectrum of sunspot. And then Bunsen and Kirchhoff realized that these are actually signatures of various chemical elements. And they also realized that when a gas is heated to a high temperature, that gas would emit at exactly the same frequencies at which it absorbs. Now the spectral lines in sunspot in sunlight spectra are absorption lines. So an implication of Bunsen-Kirchhoff theory is that if we could somehow isolate radiation coming from the hot gas near the sun's surface, then we would be able to see spectral lines which would be exactly at the same frequencies at these absorption lines. Now nature gives a way of testing this idea. So at the time of a total solar eclipse, the disk of the sun gets completely covered, and we get radiation only from the layer above the solar surface. And since radiation from this layer is more colorful than ordinary sunlight, this layer was named chromosphere. Chromos being a Greek word meaning color. So some astronomers were able to find a spectrum of a chromosphere during a total solar eclipse. And they found that indeed there are emission lines, but they were surprised that the emission lines were at frequencies totally different from these frequencies of these absorption lines. So this was a very big puzzle. So did that mean that Bunsen and Kirchhoff theory was wrong? So as I shall pointed out a little later, that Shaha solved this problem completely in his first paper. And in the fourth of his great papers, he solved another, and I may perhaps mention that out of these four papers which Shaha wrote on this subject, that first and fourth were the most important papers, which I shall discuss at some length, with a little bit of discussion of the second paper. And this fourth paper, Shaha solved even a bigger problem. So even from naked eye observations, we can see that different stars have different colors. So some stars appear reddish and some stars appear bluish. And astronomers found that stars of different colors have different spectral lines. So a big question was that whether the stars of different colors have a different composition, reddish stars and bluish stars are made out of different stuff. So Shaha solved this problem in his fourth paper. And when Shaha was working on this subject, so quantum mechanics was yet waiting to be born, but there was a Bohr-Sommerfeld model based on old quantum theory, which provided an explanation of atomic structure. And physicists already knew at that time that alkaline earth metals had 2 electrons in the outermost shell. And now it turns out that atoms which have very few electrons in the outermost shell, such atoms produce spectral lines with certain regular patterns. And so Shaha realized with astute intuition that calcium would be particularly useful for his studies, because the calcium atom has very few electrons in its outermost shell, either before ionization or after ionization. So 2 before ionization and 1 after ionization. And physicists also knew that if an element is kept in a spark, then the spark spectrum of that element turns out to be completely different from its ordinary spectrum. And Shaha gave some ingenious arguments that this spark spectrum of calcium would be just nothing but it's actually the spectrum of ionized calcium Ca+. And astronomers noted that the chromospheric emission lines of calcium were actually the lines of spark spectrum of calcium, whereas the calcium lines in the sunlight spectrum, they were more like spectral lines of ordinary calcium. So Shaha drew the conclusion that calcium must be completely ionized in the chromosphere, and that's why the spectral lines are the lines of spark spectrum. And this was a surprising conclusion at that time, because at the time most astronomers thought that the chromosphere was colder than the solar surface. Now we know that is not the case, but let me not get into that. But if the chromosphere was colder, it was thought that there would be less ionization. But Shaha realized that the pressure also would play a very important role. So here I show a table from Shaha's first paper, in which he calculated and showed the percentage ionization of calcium at different temperatures and different pressures, using atmospheric pressure as an unit. And the typical surface temperature of the sun is about 6,000 degrees. So in this line, you can see that at the 6,000 degrees, this ionization becomes increasingly higher and higher as you go to lower and lower pressure. So in this way, Shaha showed that in a chromosphere, the calcium would be fully ionized, and that's why it gives spark spectra. And he was able to do similar calculations for about other alkaline earths elements, and suddenly everything fell in place. He could give complete explanation of chromospheric and sunlight spectral lines of all alkaline earth elements. And after studying these alkaline earth elements in the first paper, Shaha turned his attention to alkali metals in the second paper. And apart from the famous sodium D lines, it turns out that that alkali metal lines are completely absent in sunlight spectrum. So the question was, are alkali elements absent at the solar surface? Now, an alkali atom has only 1 electron in the outermost shell. And Shaha realized that if the alkali atom is ionized, then we would be left with a closed outermost shell. And atoms with such closed outermost shell usually do not produce spectral lines in the visible part of the spectrum. So Shaha concluded that alkali metals are ionized at the sun's surface, and that's why we don't see their lines. But Shaha's equation also showed that if the temperature was even a little bit lower, then many alkali atoms would be non-ionized, and then they would show spectral lines. And now on the solar surface, we find patches, dark patches called sunspots, within which temperature is somewhat lower. And Shaha concluded from his equations that if we could take the spectrum of a sunspot, then spectral lines of alkali elements would be seen in that. And I shall come in a few minutes at what was the result of Shaha's this prediction. So let me first say a few words about, I think, Shaha's fourth great paper. So astronomers like Pickering and Cannon classified stars according to their spectra O, B, A, F, G, K, M. So without getting into details, let me just put the spectra of different classes one above the other. And astronomers realize that the spectral classes are not very tightly compartmentalized classes, but there are stars which have which seem to be intermediate between two classes. And as I pointed out, the biggest question was that why these different stars have different types of spectra. Was that an indication of their different chemical composition? And Shaha realized that this is a sequence of temperatures, and even if the chemical composition was the same for all these different stars, but if their surface temperatures were different, then different atoms at the surface would have different levels of ionization, and that would produce different kinds of spectral lines. And for example, it is noted that lines of neutral calcium completely disappear for stars hotter than certain B stars. And Shaha concluded from his equation that this happens at 13,000 degrees Kelvin, and so he could conclude that this type of B stars must have a temperature, surface temperature of 13,000 degrees. So considering many spectral lines and giving such argument, Shaha was able to completely map these stellar classes into a temperature scale. And today it is perhaps even difficult for us to imagine the kind of impact which Shaha's work made on contemporary astrophysics. So I give some examples from the writings of some great contemporary astrophysicists on both sides of the Atlantic. So here is a paper from H.N. Russell, the great American astrophysicist. So his paper begins with the opening line, Dr. Meghnad Shaha in an important series of papers has shown, etc., etc. And then here is a paper by Fowler and Milne from Britain, who are also leading astronomers of Britain. So the opening line of their paper is Sahas Theory of high temperature ionization has been successful, etc., etc. And here is a quote from an influential textbook, Theoretical Astrophysics, by Rosland, who wrote, "The impetus given to astrophysics by Shaha's work can scarcely be overestimated, as nearly all later progress in this field has been influenced by it, and much of the subsequent work has a character of refinement of Shaha's ideas." Well, when Shaha's fourth great paper came out, Shaha was still younger than 28. And normally, a brilliant, ambitious man of 28 would not think that his best work was already behind him. Probably Shaha also thought that he has got at last a foothold in the scientific world after years of struggle, and maybe he would achieve, he would scale greater heights after that. But unfortunately, that was did not happen. So at that stage, Shaha tried to do two kinds of research. So first of all, he wanted to do experimental verification of his theory of thermal ionization by doing laboratory experiments. And secondly, I mentioned about his theoretical prediction that alkali lines should be present in sunspot spectra. So he wanted to check whether that is the case or not. And as I pointed out that Shaha's unusual intellectual background enabled him to do his synthetic work, which required the knowledge of some totally disconnected scientific fields. Probably no other scientist in the world had this kind of a knowledge of these totally disconnected fields. But after that great synthetic work was done, the follow-up work could be done based by experts in narrowly focused experts who are working in very well-equipped labs. And let me tell you the effort of Shaha's first attempt of doing experimental demonstration of thermal ionization theory. So by making inquiries in Britain, he came to know that that the best facilities for such work existed in Nance's laboratory in Berlin, and Shaha had got an opportunity of going there. So he has written, I had written to Agar, who was Nance's assistant, and asked him to get Nance's permission for me to work at his laboratory. So I received an encouraging reply both from Agar and Nance himself, and went to Berlin in February 1921. So initially there was some kind of a bonhomie. So in a letter to Vice Chancellor Sir Ashutosh, Shaha boasted, I have succeeded in experimentally demonstrating that gaseous atoms can be ionized simply by heat, temperature ionization of gases, an effect which under various forms have been looked for in vain but by such eminent physicists as Maxwell's, Hittorf, Rayleigh, and J.J. Thomson. The experiment will shortly be published in the Zeitschrift für Physik, and either myself or Professor Nance will announce it before the forthcoming meeting of the German physicists at Jena, where I also have an invitation. But very surprisingly, this paper which Shaha promised to Sir Ashutosh never materialized. And in fact, there was not a single publication from Shaha during his stay in Nance's laboratory. And I don't know the reason for that. So after Shaha came back to India, he almost shifted from Calcutta University to Allahabad University. And after he was elected a fellow of the Royal Society in 1927, so he received a grant from the government of that province with which he could set up his ionization experiment at Allahabad University. But again, the result was not spectacular. It led to only one short paper in an international journal. Now, the furnace which Shaha fabricated for that work still lies there in a basement laboratory of Allahabad University. So here you can see me standing next to the furnace, and here is a diagram of the schematic diagram of the furnace, even in that paper of Shaha. So now I come to the second effort of Shaha. He tried to verify whether his theoretical prediction is correct, that there would be spectral lines of alkali metals in the spectra of sunspots. So at that time, Mount Wilson Observatory near Los Angeles had the best facilities for doing this kind of work. And Shaha wrote to the distinguished astronomer Hale, who was the founder of this Mount Wilson Observatory and was the director till that time. So Shaha wrote, I believe that these theories explain a good deal of the valuable data accumulated during the last 40 years by the American and English astrophysicists, and besides open up new paths of investigation. I append herewith an account of some investigations which may be immediately taken up. So I shall be very glad if someone at Mount Wilson Solar Observatory undertakes the work suggested overleaf. My means are too limited, and as my university is very poorly provided for astrophysical work, I see no prospects of ever being able to carry out the ideas contained in my papers. So probably Shaha did not know that Hale had become a serious patient of schizophrenia, And in fact, he was forced to resign from this directorship, more or less at the time when Shaha wrote to him. So this letter fell in the hands of the Princeton astrophysicist H.N. Russell, who was a regular visitor to the Mount Wilson Observatory. And Russell replied to Shaha, and you may note that the date of a reply was less than a month from the date of Meghnad Shaha's original letter. So Russell wrote, Dr. Hell has shown me your recent letter to him. Your predictions about the lines of alkali metals have been completely verified. Rubidium is present. We will investigate cesium as soon as proper photographs of the spot spectrum near lambda 8500 can be obtained. So very shortly, within the next few months, or perhaps within the next few weeks, Russell verified all of Shaha's predictions and wrote several extremely important papers in which he heaped on very high praise on Shaha as a pioneer and gave him full credit. So probably these papers produced some kind of a mixed reaction in Shaha. On the one hand, he must have been happy that his theoretical predictions were being verified and he was being given full credit as the pioneer. But he also must have realized that the scientific field which he had pioneered had already gone out of his hands, and probably he would never be a leader in that field again. So some of his Shaha's admirers in the West wondered why, after this very short era of extremely brilliant papers, these 4 papers on thermal ionization, then why Shaha was not able to produce more work of such class. So in this long autobiographical letters to Plaskett, Shaha describes some of the difficulties he faced at Allahabad University, and presumably these letters are seen by many other astrophysicists. So Russell, who was an admirer of Shaha, wrote to Shapley, another admirer of Shaha, I had often wondered why Shaha's activity in the theoretical field fell off after his return to India, and his account gives the explanation. His recent contributions to theory do not seem to me to be at all of the same importance as the old. His history affords a very good argument that the Indian universities and perhaps the government should be actively interested in securing proper opportunities for men of proven ability. So perhaps the last sentence could be written even now. So as Shaha's admirers came to know about the difficulties which Shaha faced after returning to India, they also wondered whether Shaha might have been able to do his early brilliant work under these difficult conditions in India. So as I pointed out, that almost immediately after finishing this work, Shaha came to work in Fowler's laboratory in London. So it was widely believed that maybe, I think Shaha did this work when he was an assistant in Fowler's laboratory. And Shaha was particularly sensitive about that. So when Plaskett suggested this in an article, then Shaha wrote this long autobiographical letters to Plaskett, giving an account of his scientific career and pointing out that he did this work completely on his own before he ever stepped out of India. So after receiving Shaha's letter, Plaskett immediately wrote back. So what was quite new to me was the fact that the early part of your work was done in India, not Germany, before you came to Fowler's laboratory. The knowledge that you had done so much without help and backing in India only serves to increase the admiration I have always felt for you for your great contribution to astrophysics. And even Russell, who had exchanged several letters on Shaha, was not aware of that. So he wrote, I do not think I knew till seeing this letter how much he had done previously in India. So as Professor Chandrima Shaha mentioned that afterwards Shaha made tremendous important contributions to Indian science by establishing many organizations and which were pivotal for the growth of Indian science. But Shaha was never to reach again that very rarefied height like this height of Kanchenjunga, where very few of the greatest scientists reach. So to conclude, Shaha's story is simultaneously a story of triumph and defeat, a story at once uplifting and tragic. So Shaha showed that what a person from a humble background in an impoverished colony achieved through his sheer intellectual power, but his inability to follow the trail which himself has blazed also showed that there are limits to what even an extraordinarily brilliant person can reach under very trying circumstances. And I end by pointing out that this lecture is based on a more fuller paper, which is available at internet. So it gives many details which I could not cover in this talk. So thank you.
Thank you. Thank you, Professor Choudhuri, for a wonderful exposition on Professor Shaha's work. And I'm sure that people will have questions. Can we start? Can you unshare your slide?
Okay, sure. Let me unshare. Okay, let me share. How do I? Yeah.
You go to share, and then there will be a little.
Yes. Okay. Yeah. Yes. Stop sharing. Okay. Sure. Yeah.
So, Dr. Nautal, did you get YouTube? There are any
In
questions?
YouTube, there are no questions. Commander, yeah, there is one question by Dr. Dwivedi. Yeah.
Yes.
Dr. Tata here.
Dr. Tata. Yeah.
May I speak, Dr. Tata? Yeah.
Yes. Can you ask?
Yeah.
Can you?
A very wonderful lecture and very informative. I really liked the way go back in time. Okay. But one thing, but he was very excelled in his theoretical ideas and converting into equations, etc.
Yes.
He went to abroad and came back. Then he wanted to test through experiments. By the time Raman also was doing some experiments, but
Yes.
Raman was successful through experiments. But somehow, why was that the experiments initiated by him could not take off and earned some name or fame to him? Can you throw more light on it?
Okay, that is an interesting question. You know that now physics is fragmented, and nowadays it's theoretical physics and experimental physics have become almost like two different disciplines, and very rarely somebody does research in both. But 100 years ago, this division was not so clear. And both, I think, Meghnad Shaha and Sottenborg, they felt that because they had also to teach students and develop a scientific tradition in India, they both were strong in theory, but they both had a conviction that they should also do experimental work, which is important for the country. And there is some indication that when Shaha first joined Calcutta University, he himself tried to do some work in under supervision of Raman. And in one of the reminiscence papers, Shotten Bosch mentioned that Shaha tried to do this experiment, and C.V. Raman was not very pleased because Shaha did not have good experimental skills, so he did not have good skills with his hands. So I don't know. So Bosch was his classmate and saw him closely, had that assessment, and maybe that was one reason why Shaha was not so successful in experiment. And in the case of Shotten Bosch, also the same thing. After his famous theoretical work, he felt that it was his job to develop an experimental tradition in India. and he also did physics experiments and using X-rays, and he also did tried to do some organic chemistry experiments. And to the best of my knowledge, that Shotten Bosch was also not very, I think, successful in his experimental studies, and certainly C.V. Raman was a master experimenter.
Yeah. Okay. I just one small question. Was Saha has his students worked with him? Are there any Indian students?
Yeah, Shaha produced several students. So some of his perhaps his most famous student was D.S. Kothari, and he had
Okay. Kothari
worked
Fellowship. Okay.
several other trained several others. I believe Kothari was also a past president of INSA, if I am not mistaken.
Yeah.
Yes.
Thank you. Thank you very much.
Dr. Actually, I often, we read that his work should have gotten the Nobel Prize.
Yes.
Why do you think that did not happen? Because of any other than science, some activities other than science?
Oh, well, other his activities, I think that was an interesting question. That played a role when he was elected fellow of the Royal Society. And in fact, Royal Society preserves its archival materials very well. And when he was nominated to the Royal Society, I think there were some inquiries. It was some persons pointed out that in his youth, Shaha had connections with revolutionaries, and Royal Society made some inquiries whether Shaha really had connections with some revolutionaries. And some officials in India, they sent the information to Royal Society that Shaha indeed had some connections, and it may be awkward for Royal Society to elect Shaha. So it is a greatness of British scientists that even after getting this negative recommendation, some of the great British scientists decided that in spite of this background, Shaha should be elected to the Royal Society because of his science. So that is something that when we criticize the colonial rule, we should also remember that some of the British scientists could rise above this pettiness and could appreciate the greatness of Indian scientists. Now coming to the question about Nobel Prize, so there was so in these early decades of 20th century, the Nobel Prize was never given for work in astrophysics, and there are various stories why that was the case. But let me not get into the stories. So Meghnad Shaha was nominated several times for the Nobel Prize, and it is surprisingly that it was the year 1930 when he was shortlisted for the Nobel Prize, along with in the same year in which Raman was shortlisted.
Okay.
And it's Dr. Rajinder Singh will give another lecture in INSA in a few days. So he has looked at this archives of the Royals of the Swedish Academy for Nobel Prize, and he has analyzed this issue that apparently there are three shortlisted persons: Raman, Meghnad Shaha, and somebody else. And Royal Society got opinions of these scientists from many of them, and I believe eventually this Royal Society, the Nobel Committee at that time thought that Shaha's work is more for astrophysics rather than fundamental physics. So other great astrophysicists of that era, like Eddington and Hubble, also did not win the Nobel Prize.
I see. Yeah. But that clause of his being connected to revolutionaries was not a reason why he did not get the prize. Or, the Royal Society did recognize him with an FRS.
So as far as I know, that was not the case for the Nobel Prize. Of course, we know that Mahatma Gandhi was also nominated for the Nobel Prize for on various occasions, and presumably the British government put some pressure on Swedish Academy not to award him for the Peace Nobel Prize. So So there are, I think, sometimes such issues play a role, but I believe for the Nobel Prize, this Shaha's connections with revolutionists probably did not play a role. It was more like his work was thought of more of astrophysics rather than basic physics. So what you should ask Rajinder Singh more about that. He has studied this question in detail.
Yes.
Can I add Jagannathan here?
Yes, Jagannath, please.
Yeah, this is more or less the same story like why GN Ramchandran didn't get it. I mean, in spite of his five-side plot being used left and right by everyone for confirmation, they were, I think, looks like talking, okay, single thing, we have given double helix, we have given, so what about triple helix? But then the five-side plot is much more important in protein. I don't know. The same, other than science, I think played a major role in GN Ramchandran.
In GN Ramachandran's case.
Yeah.
So I believe that for Nobel Prize, there is one requires quite a bit of lobbying. So
Yeah.
I vaguely heard that in some of the top American universities, so often if they have a strong candidate among their professors for a Nobel Prize, they often do extensive amount of lobbying. And certainly in countries like India, which we cannot do that kind of a lobbying, and so that is so certainly this scientific communities in more well-connected countries have certainly have an advantage. And probably more than science, that is often true more for literature. I think literature Nobel Prizes have been often very questionable.
And peace.
Thank you so much for a very, exhaustive explanation, and the others' work also that you quoted. It made it easy to understand a lot of it. So thank you very much for giving such a wonderful lecture. So anyone else who wants to come in?
I just wanted to say that Eddington, one of the greatest astronomers, he termed this work by Shaha as one of the most important discoveries in astronomy since introduction of telescope by Galileo.
Yeah, I think he was asked to write an article on astrophysics in one of the early editions of Encyclopedia Britannica, and I think he made a list of 10 or 12 most important works in astrophysics from Galileo's time, and he listed Shaha's work as one of them.
But even within our country, Saha is not such a popular name as, say, Einstein has become all over the world. So, of course, there is no comparison that way. But even within India, not many people know about Saha's work. Why is that so? Shouldn't we promote his work or contribution?
Maybe.
I would almost say it is other way around. I think in that era of Indian independence, I think there is the even general public were very much concerned whether India can reach great heights in science. And I think this Jagadish Bose, Prafulla Chandra Ray, and Raman Meghnad Shah and Satyen Bose, they were all, I think, important. Their names were known to quite a large extent to the general Indian public. But somehow I would say that after independence, that has not happened. So there is a mention of G.N. Ramachandran. So I would say that G.N. Ramachandran is not at all known the way he should be. Probably scientists of that earlier era, Shaha or Bose, they were more well known compared to scientists of such great scientists of later era like G.N. Ramachandran.
Yeah, that's the story of many scientists that, somehow, like you said, that Bose, Jagadish Bose, Satyen Bose, and Meghnad Saha, they were sort of iconic figures in Bengal, at least at that point of time. And then the rest of India also knew, and the people were less, but, they had a lot of impact on the psyche of people that they were doing great science. And so they were more known pre-independence era than after independence. And as population grew, it started getting diluted, and less people were knowing about scientists. And so, like, yes, of course, G.N. Ramachandran should be known more than how people know him. But this is something that we have not been able to really do, is to tell people, tell them the stories about these scientists and let them know. Like, I'm not sure if in school curriculum there are these kind of stories that are given to read to the students.
But the reason I said this is that people follow the role models. The society follows the role models. We have to create role models like Saha or G.N. Ramachandran and others, so that people like to follow them, not just the cricket stars and film stars.
Yes.
Just one question. Is it okay?
Yes, please.
Yeah. Because Saha Institute, because I was from DAE. Currently, I'm at University of Hyderabad. So when Homi Baba was there at the helm of the affairs, we were not even taught. I was from 25th batch. Saha Institute was there.
Yes.
It was recognized on his name. But in the subject part, whether in nuclear physics or in atomic physics or spectroscopy, Saha was not taught in any of our textbooks. Similarly, in DAE also, we were not knowing much about Saha except the Saha Institute's name.
Yes.
Is the Homi Baba and Saha are related scientifically through anything, or it was not recognized by him?
Well, it is a very, very interesting question. In fact, there is an outstanding scholar, Canadian scholar, Robert Anderson, who wrote a masterpiece on this subject, I think, of development of scientific organizations post-independence India. I think Shaha, Bhabha, and Bhatnagar, these are the three persons who played a key role. So this book is about the contributions of these three persons. And somehow I think Shaha had a sort of a more at one time. I think Shaha was also involved in the freedom movement, and he was a good friend of Nehru. But somehow in later years, I think Bhabha had more of an ear of Nehru, and Shaha was sometimes bitter about that, and there was more support given to TIFR and much less support given to Shaha Institute. And of course, one should look at the other point also. Probably Bhabha had more leadership qualities than Shaha in building such an institute. So although we know that that Shaha established so many outstanding institutes, but one also has to give recognition to some of Shaha's weaknesses, that in his organization he would sometimes try to push his students and even his son. So there is an interesting letter between Bhabha and Shaha, which I have seen, where Bhabha has gently tells Shaha that you should not push your son too much, let him establish himself. So Shaha also had these weaknesses, and perhaps Nehru realized that, and that's why he gave more support to Bhabha. So anyway, this wonderful book, Nucleus and Nation, is a large book devoted by Robert Anderson, devoted to this subject completely. And maybe Professor Chandrima Shah may also think of inviting Robert Anderson to give a INSA lecture.
Yes, thank you. Yes, I've been reading that book. I mean, you have to take in a lot. I mean, there were so many instances, totally history of Indian science. It's a very good book. Yes.
There is a question on YouTube by Dr. Rahul Vagasia. And the question is, after development of quantum mechanics, how Saha's ionization equation stood out with respect to this new change?
Okay, so Shaha's ionization equation basically, follows from basic principles of statistical mechanics. That's a somewhat of a technical question. One has to calculate a partition function of a gas, and from that partition function, one gets that. So it even after development of quantum mechanics, I think these things stand up. So I think it's a little technical point. I think in quantum, after formulation of quantum statistics, it was realized that in a partition function you have to put there should be terms of corresponding to many atomic levels, and Shaha's theory was based by considering only the leading term of the partition function. So there are some I think some corrections by other scientists after Shaha's work, but the basic framework of the theory stands, though there have been some corrections and modifications.
Any more questions? There are some appreciative words in the chat box about the lecture from some people, but there are no more questions here. Anyone would like to ask any questions or any doubt?
Dr. Nautiyal, can I ask, make a comment?
Please,
Yes,
please.
please.
So Arnab, it was a nice talk. Since somebody else also asked about this point, your main topic was Saha's ionization equation, but though the whole topic is not that easily communicated in most of the MSc texts or things like that, but one should also remember that anybody later after MSc doing stellar astrophysics or spectroscopy for that matter would very well know about this Saha's equation. So yes, it was somewhat focused topic in most of these studies in MSc and beyond, but yes, it is quite well known to all the stellar spectroscopists. So I thought I would just mention that, even though it's a very limited in that sense, but yes, it is known to a major community of stellar astrophysicists. Thank you.
But I would say that even in many well-known textbooks of statistical mechanics, such as a book by Rife or by Landau and Lifshitz, this topic is discussed, and it is I believe that many of the Indian universities is a part of MSc syllabus. So when I taught the course on statistical mechanics at IISc, so I certainly covered Saha ionization equation. Of course, only the physics part of it, not the historical part which I discussed today.
Yeah, true. Just like, the Bose-Einstein statistics, for example, it is probably more popularly known in many of these teaching courses, but Saha's equation were a little less compared to that. Yeah.
Oh, thank you, Professor Ranjan Gupta. Any more questions? Of course, a lecture like this generates a lot of interest and a lot of comments, and we have seen a very good discussion. But we have a time limit. If there are any more questions, they could be sent to INSA or directly to Professor Rai Choudhuri. Ma'am, anything else except the formal vote of thanks?
No, I think we can go for the vote of thanks now, since we do not have any more questions.
This is a matter of pleasure to thank everybody who contributed to the program. Professor J.C. Bhattacharya had described Saha as a freak of nature, a statistical rarity, a human being born with an intellect, energy, and determination of several orders of magnitude higher than normal. And I think this caricature of Professor Saha has been beautifully stated and described by Professor Arnab Rai Choudhuri. We are very thankful to you, Professor Rai Choudhuri, for this beautiful lecture. And I think every one of us enjoyed that. We are thankful to Professor Shaha, the president of INSA, who has conceived this program. And on the birthday of Professor Aman Shaha, she took the initiative and invited Professor Rai Choudhuri. Dr. Seema Mandal, Dr. Arora, and Mr. Zokarkar of INSA, along with Mr. Karthik and his team of IT, have done a wonderful job in coordinating the whole thing. On behalf of INSA, for thanking like ourselves, but I would like to express the words of appreciation for them, and very much sincere thanks to the audience who joined. I think this is the highest number we have seen in the series so far of the people who have attended this. And there are a lot of people who are seeing it on YouTube also. And it will continue to be available on YouTube for those who have missed it today. So I again thank all those who have attended, to all those who have joined the discussion and added to the beauty of the event. So once again, thank you so much. Thank you, Professor Raichaudhuri and everybody.
Thank you.
On 22nd, we will have another program, and that will be a webinar by Dr. Rajendra Singh. He's in Oldenburg, Germany, and he'll be talking about a very interesting topic, which Dr. Raichaudhuri also just mentioned. So please be on lookout, watch the Facebook, our website, and all our social media sites for the next program. Thank you so much. Goodbye. Stay safe.
Thank you. Thank you.